So in class we discussed Lewis structures, and we said that a Lewis structure, it shows the 2D arrangement of the molecule, showing the bonds and lone pairs of the electrons. And remember, a lone pair of electrons are the pairs of electrons that are not involved in a chemical bond. So let's just go to the examples and let's follow the little steps or the strategy we discussed earlier. So let's look at a simple diatomic molecule here with hydrogen. So we have H2. So step number one is to count the total valence electrons. Now, since hydrogen is 1s1, it's going to have one valence electron. There's two atoms there of hydrogen, so we're going to have two total valence electrons in our molecule. Now, this one, since we only have two atoms, we're just going to write them next to each other. That'd be the only way to arrange them. Now, even though this is for a simple little molecule, I want to follow the same strategy. Now, step two is to predict the arrangement. We did that. Step three is to always start by attaching with single bonds. We did that. Let's remember that a single bond represents two shared electrons. Okay, the next step is to fulfill the octet rule. Now, we need to remember that hydrogen is one of the exceptions to the octet rule. It only wants to share two electrons, so it can get to that 1s2 full orbital or full electron configuration. So we are fulfilling the octet rule really for hydrogen because it's an exception. Next, we are going to add lone pairs if we need to. We don't need to there. Now let's make sure that our picture matches our number. So I have 2 electrons right here. I have 2 electrons right here. So that does match. So this would be the Lewis structure for a hydrogen molecule. Okay, now next, let's look at fluorine. Step 1. Since fluorine is 1s2, 2s2, 2p5, we're going to have 7 valence electrons. So we have 7. We have 2 fluorine atoms in this molecule, so 7 times 2. That means we have 14 valence electrons in the whole molecule. Okay, now step 2, let's arrange the atoms. Since we only have 2 atoms again, we're just going to put them next to each other. So fluorine and fluorine. Next step, let's attach them with single bonds. So there's our single bond. Single bond represents 2 electrons. The next step, let's fulfill the octet rule. So we have 2, 4, 6, 8. To fulfill the octet rule, we're going to add lone pairs of electrons around the 4 sides of the atoms. Now this fluorine also needs 2, 4, 6, 8 electrons. Okay, now we're fulfilling the octet rule. Now next step is to check and see if our picture matches the valence electrons we have available. So let's count. 2, 4, 6, 8, 10, 12, 14 electrons. That matches. This is the Lewis structure for a fluorine molecule. Let's go down. What if we combine these two things and we had hydrogen fluoride or this hydrofluoric acid? So let's count the valence. We got 1 from the hydrogen, 7 from the fluorine. So we're going to have 8 valence electrons in this molecule. It's a diatomic molecule again, so we're going to put hydrogen next to fluorine. We're going to start by adding single bonds. Next, we're going to fulfill the octet rule, but remember that hydrogen only wants 2. It already has 2. So let's fulfill it for fluorine now. 2, 4, 6, 8. Next, let's make sure that our picture matches our number. 2, 4, 6, 8. It does. So this would be the Lewis structure for hydrogen fluoride. Okay, next, we have boron trifluoride. Boron has 3 valence electrons. Fluorine has 7 times 3. So we get 24 valence electrons in this molecule. Now we need to remember that boron is one of our other main exceptions. We saw up here in our picture that boron has 3 valence electrons and would really love to share another 3 to match these up. So boron wants 6 valence electrons total. So let's get boron in the middle. So when I say arrange the atoms, it's usually the case that that first atom in the compound will be placed in the middle. Okay, let's put the fluorines around it. And we attach with single bonds at the beginning. Okay, next, let's make sure everyone's fulfilling the octet rule, except for boron, who already has 2, 4, 6, already good. So we're going to get 2, 4, 6, 8 around this fluorine, 2, 4, 6, 8 around this fluorine, 2, 4, 6, 8 around this fluorine, and boron's good. Okay, now that everyone is fulfilling the octet rule, let's see to make sure that our electrons in our picture match the ones we have available. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this is the Lewis structure for boron trifluoride. Okay, down here, carbon tetrafluoride. Step 1, carbon has 4 valence electrons. Fluorine has 7 each, times 4 fluorine atoms in this molecule. So we end up with 32 valence electrons. Now again, when we're going to predict the arrangement, let's put the first atom in the compound in the middle. So we'll get carbon in the middle here. Let's put the fluorines on all 4 sides. Now let's attach them with single bonds. Now let's fulfill the octet rule. Now look at carbon. It's already got 2, 4, 6, 8. Carbon's good. Let's just leave it. Okay, now the fluorines. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, now everyone's fulfilling the octet rule. Now let's make sure that the electrons in our picture matches those available. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now I usually go in this little roundabout fashion and try and make sure I'm not missing anything. So this is the Lewis structure for carbon tetrafluoride. Next, nitrogen tribromide. Okay, nitrogen has 5 valence electrons. Bromine has 7 each, times 3 in the molecule, would be 26 valence electrons. Okay, nitrogen's going to go in the middle. Let's put the bromines on 3 sides. Now people sometimes ask, does it matter which sides the bromine goes on? And I'd say it doesn't matter, because at the end of the day, we're really going to be looking at these molecules in 3 dimensions and not 2. So we can leave it anywhere you want. And if you want it to be somewhere else, just rotate the page and you'll get it there. So let's start with single bonds. Let's fulfill the octet rule. Now nitrogen has 2, 4, 6. So let's add another lone pair of electrons on the bottom there. Bromine has 2, 4, 6, 8. This one has 2, 4, 6, 8. 2, 4, 6, 8. And now we fulfill the octet rule. Okay, last step, let's make sure the valence electrons in our picture match our number. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So it matches again. Okay, silicon trihydride. Silicon has 4 valence electrons. Hydrogens have 1 each, times 4. So we have 8 in our picture. Let's put silicone in the middle. Let's organize the H's around it. Let's start with single bonds. And this one's easy to forget that. Let's not forget that the hydrogens only want 2. So look at this. Each hydrogen is already stable. So we leave it. Silicone has 2, 4, 6, 8. So it's good. Now let's count to see if the picture matches those available. 2, 4, 6, 8. We're all good. So this is the Lewis structure for silicon tetrahydride. What about NO3 minus? Oh, look at this little guy right here. Remember that a negative ion means that the molecule or the atom has gained an extra electron. So when we're counting, we need to add 1 electron to our number now because of that. So nitrogen has 5 valence. Oxygens have 6 each. There's 3 of them, and then we're going to add that 1 because of that ion. So 18, 19, we get 24 electrons in this molecule. Let's put the nitrogen in the middle. Let's keep the oxygens on 3 sides. Let's then start with single bonds. Let's fulfill the octet rule now. Give everyone 8. So nitrogen wants 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And right now I'm going to take a little time out because we're going to skip to the second video to finish this one up.